Okay, so now that we know what the R squared is, it is also important to warn against its use a little bit, or at least highlight the importance of qualifying the R squared a little bit more. And that is done with a so-called F-test. And what an F-test does is to look at the overall significance of a model. So are all the independent variables together statistically significant? And of course, so far we have only looked at the bivariate regression. So in other words, so far we only looked at a regression where we had y I predicted by an intercept beta 0 and then a beta 1, and then we had a variable x1, and that's it. But what you could do is, of course, you could add many more. That's a 1. So you could add many more independent variables, like there's an x2 I, or there's a third variable, or a fourth, and so on. Now typically you don't see regressions where you have more than 8 or 9 independent variables. And the reason is, if you have a dependent variable that you want to explain, let's say I want to explain why a country has a higher GDP per capita. I can throw in many independent variables. I can say maybe beta 1, that's the coefficient for how much capital do they have. Beta 2 is maybe about the political system. Are they a democracy or are they a autocracy? I can look at maybe demography. Is it a young society, an old society? I can look at education. I can look at health. And theoretically, I can add also many bogus variables. I can, for example, add a variable that says, okay, how many kilometers is it from the country's capital to the nearest beach, and create that a variable. Or another bogus variable, which is how many vowels are included in the country's president's name, and add that as a variable. Or I can add, I don't know too many bogus variables, but imagine you can come up with all kinds of variables and add it and add it and add it and add it and add it, and then by pure chance, by pure randomness, those variables will explain something. But if you run a regression with like 100 nonsensical variables, like how far away is the capital's airport from the nearest beach, yeah, it will explain something, but it's probably not as good of a variable as how much capital does a country have, or what is the quality of the political regime. So in other words, I can increase the R squared by simply adding many independent variables, but each independent variable is a little bit useless. Okay, so that's the basic idea. So again, why the R squared could be misleading, and I like to illustrate it in the pebbles/rocks bucket analogy. So especially in multivariate analysis, one could artificially drive up the R square by including many independent variables. This is what I just tried to illustrate. And the way you can think of regression analysis you want to explain something. And what is explaining something, think about it as you want to fill up a bucket. And you want to fill up that bucket with pebbles or rocks. So then filling up the bucket is the equivalent to wanting to explain something. So that's the metaphor. And the pebbles are the explanatory variables, and how much you can fill up the bucket, that is how much you can explain with your pebbles. So, and again, one can fill up this bucket with a bunch of very small pebbles, and one will get a high R squared. But one could also fill up the same bucket with big pebbles, which in this case are more like heavy rocks. And a good model is one that fills up the bucket with a few heavy rocks. So here you can see a bucket where you have many small pebbles in there. And they also, partially overlap. And that is probably giving you a high R squared, that model, but it is not significant in its entirety. So, because each little pebble really doesn't explain anything. So, if you compare this bucket filled up with a bunch of small pebbles to something like this, you immediately see the difference that here we fill up the bucket with a couple of explanatory variables, which are all very meaningful by themselves. So, and meaningful by themselves would mean, imagine we take out one explanatory variable from that bucket. Well, then the bucket will become substantially less filled. Whereas in the previous example, if I remove one little pebble from there, it's barely noticeable. So that is why what you see here now, that is a meaningful model in terms of the pebbles / rock filling up the bucket analogy. And what you see here as an example, or as a way to think about it, that can also be tested. And that is done with a so-called ANOVA table. And the ANOVA table already draws on many things that we already know from R squared. Most notably, it draws on the explained sum of squares and the total sum of squares and the residual sum of squares. So, and first of all, ANOVA stands for analysis of variance, and an ANOVA table, again, builds on what we already know from calculating the R squared, namely the explained sum of squares, the residual sum of squares, and the total sum of squares. Yet, whereas the R squared only looks at the ratio of the explained sum of squares to the total sum of squares, the so-called F statistic, which builds on ANOVA, or which is derived from an ANOVA table, looks at the explained sum of squares and the residual sum of squares and the total sum of squares as some form of an average. And technically, we average out the explained sum of squares and the residual sum of squares. We average them out over the degrees of freedom that we have. And then we get an F statistic. And the F statistic is the explained sum of squares divided over the number of coefficients that I have minus 1. And the residual sum of squares are averaged out over the number of observations I have in my sample minus the number of coefficients. And that gives an F statistic. So, and maybe just a note on the side. So we have already seen a normal distribution. And a normal distribution looks somehow bell-shaped. So let's say I have a variable, so this is normal. Let's say I would square that variable. So let's say in a normal distribution we may have negative and positive values. But now I square a variable which is normally distributed. Well, all the negative values, they will become positive. So basically you can think of that you throw those negative values on the positive, into the positive range when you square. So now, if you square a normal distribution, then we get something which we call a chi-squared distribution. So a normal squared is equal to a chi-squared distribution. And it looks like this. And an F distribution is the ratio of two chi-squared distributions. And an F distribution can also have different shapes. Like can look like this maybe, and it depends on the degrees of freedom. The greater the number of coefficients, the greater the number of observations in my sample, the greater the n, the more it looks normal. So the ratio of a chi-squared 1 over another, maybe 1 over a second chi-squared, so the ratio of two chi-squared distributions, that gives you the F. And you see the explained sum of squares, well, that is something always squared. The residual sum of squares is always something squared, but now we take the ratio. So the ratio of two chi-squared distributed variables, that gives you a so-called F distribution. And the exact shape of the F distribution depends on the degrees of freedom that we have in the numerator, the explained sum of squares, and the degrees of freedom in the residual sum of squares. And again, the degrees of freedom in the numerator for the explained sum of squares, that's the number of coefficients minus 1. So in a bivariate regression, we have two coefficients, the intercept and the slope. So two coefficients minus 1, we have only 1 degree of freedom. But in a multivariate regression with, I don't know, 10 slope variables or 9 independent variables plus the slope, then we would have to subtract 10. Then we have to subtract from the 10 1, and we had 9 degrees of freedom. So the degrees of freedom for the regression is the number of coefficients minus 1, and the degrees of freedom for the residuals, that is the number of observations in the sample minus the number of coefficients. Okay, so now let's take a look at an ANOVA table. And that is what it looks in general terms. So what you will see is the sum of squares. Those sum of squares we already know from the calculation of R squared. So we have the sum of squares for the regression. That was the 22. And then we had the residual sum of squared. That was 10. The total sum of squares was 32. Then we report the degrees of freedom. Well, the regression was based on two coefficients, an intercept and a slope. That means we have 1 degrees of freedom. The residuals have 4 degrees of freedom because our sample had 6 observations, but we need to subtract the 2 estimated coefficients. Then in the next column, we average out the sum of squares by their respective degrees of freedom. And then the final step is that we calculate the F ratio as the ratio of the mean sum of squares for the regression over the mean sum of squares of the residuals. So in our example, we had the sum of squares, the explained sum of squares, ESS. That was 22. We have 1 degrees of freedom. So then if we square that out, on average, that means we have 20. So the way you can think about it is, if you have only one degree of freedom, which means two regressors, the intercept and the slope, well, each coefficient explains a lot of the sum of squares. Well, if you have the same sum of squares, but you need to distribute it over, let's say, 50 little pebbles as explanatory variables, and you have only 49 degrees of freedom, then the mean sum of squares, the average explained sum of squares per coefficient, becomes very, very small. Okay, so the higher the mean sum of squares is, the more each regressor explains. And again, you can think of it as the pebbles. Well, the bigger is the ESS, or the mean sum of squares. For the coefficient, well, the bigger the pebble is, the more it is a rock. For the residual sum of squares, we take the residual sum of squares that used to be 10. And now think of the degrees of freedom. The degrees of freedom are, in our case, 6 over the two coefficients, so 4. So now we have here a mean sum of squares of 2.5. But now imagine we had many, many more observations, maybe 100. But still, we had only a residual sum of squares of 10. That means averaged out over the degrees of freedom, which is essentially closely related to the number of observations, then means each observation carries a very low error term. So now what we want in order to get a very significant model is, we want the mean sum of squared per regressor to be very high, and we want the residual sum of squared, essentially per each residual, to be very low, and then we will get a high ratio. And the higher the ratio is, what it means in words is that there is a lot of explanatory power in each coefficient or in each regressor, and the lower the mean sum of squared for the residual is, what it means is, well, the closer the actual observation is to the trend line. That's what it essentially means. So what we want is a very, very high F ratio. Then this indicates, when the F ratio is very high, that our model in its entirety is very significant. And you see, for example, going back to the R squared, if the ESS is distributed over, let's say, 10 regressors, I have 9 degrees of freedom, well, then the numerator of the F ratio becomes very small, and I may have a very high R squared, but I probably don't find that this model is highly significant in its entirety. So now our F statistic is 20 over 2.5, which is 8.8. So now how does an F statistic work? So we look at the F distribution, and the F distribution can have a different shape depending on how many degrees of freedom we have. And I can show that to you in a minute in Excel. But let's just continue with our F test. Just like any hypothesis test, we would have a null hypothesis and an alternative. When it comes to the F test, we would say the H0 is that the model in its entirety is, colloquially speaking, useless. It doesn't explain anything. Or, in terms of the pebbles analogy, there's only a bunch of small pebbles in there. So model in its entirety is useless, and the alternative is model is useful, meaning you have a bucket full of rocks. Okay, so now what we do is we do an F-test, and our F statistic was 8.8. So that is maybe somewhere here, maybe that's 8.8. And you can see what that tells you is, let's say we have an alpha of, let's say, 5%, we will say if the probability of our sample that generates an F statistic of 8.8, if that came from a true population where there is really no relationship between the variables, so the explained sum of squares and the residual sum, they should be all zero or close to zero, nothing is being explained, then if that is highly unlikely to come from a population where all those regressors really don't explain anything individually, then we would reject the null. And in this case, the area, we can barely see it, but if let's say our alpha is 5%, from our F statistic of 8.8, we can clearly tell that this is probably a probability of less than 5%. So our sample, where our regression generates basically, so the correct way to say it is, okay, so we got a sample of 6, and the two regressors explain on average, 22, and the 6 residuals explain together 10, to get something like this from a population where there is presumably no relationship between the variables. That is extremely unlikely. And because it is extremely unlikely, we reject the null that the model in its entirety is useless. Okay, so now what is actually that probability? Actually, before I show you that, let's quickly introduce some other things. So again, when it comes to an F-test, the hypotheses are the null list, the model in its entirety does not explain anything. The alternative is the model in its entirety explains something. So what is your alpha? So let's say your alpha is 5%, so 0.05. So now what is the critical F-score at which you would reject? And the answer is 7.709. And we got that by using Excel. And we insert the formula f.inverse.rt 0.05, that's the p-value. And then Excel wants to know degrees of freedom 1. And those are the degrees of freedom of your ratio that you have in the numerator. And then Excel wants to know the degrees of freedom that you have in the denominator, and that was 4. So now for the alpha equals 5%, we get the critical value of 7.7, but our F statistic is clearly in the rejection zone. So therefore we reject the null hypothesis that our model in its entirety is useless or does not explain anything. But again, we could have made a type 1 error, and the corresponding p-value is determined in Excel by simply looking at f.dist right tail. So we want to know what's the probability to the right of our F statistic of 8.8. And in this case, it is 0.041. And now it's just like an interesting thing about statistics. Whenever you have a bivariate regression, the p-value of the F-test is always equal to the p-value of the slope coefficient. Okay, but we can look into this again later. So let's take a look at the actual F-test. So we can see our critical F was roughly 7.7. That means to the right of 7.7 we have underneath the F distribution a 5% probability mass, even though we can barely see it. And our F test is clearly in the rejection zone because our rejection zone begins here. So that is the rejection zone. Okay, so to the right of our critical F, we have 5% probability mass, and to the right of our and to the right of our test statistic, the 8.8, we have roughly 4%. Okay, what I still wanted to show you is if you take a look at the F distribution in Excel. So let's say I want to draw something, the F value for, let's say, from 0 maybe to 9, that should be good enough. So go to Edit, Fill, Series, maybe step value 0.1, and I want to stop at maybe, let's say, 10. Okay, so then I can draw the F probability density function, PDF. And for this we use the command F dot, and then you can already see there is something called F dot dist. Okay, and then I want to know what is the value for X. Okay, that is 0. For this one specifically, we will get now an error term because the F distribution doesn't have a value for 0. But when we copy down, there will be values. And then it wants to know, Excel, what's the degrees of freedom in the numerator. And we said 1. But what I do is I just put that quickly as a variable that I pick up from here. I just create the degrees of freedom, the numerator, that's 1, because I want to change it and show you how the distribution changes. And the degrees of freedom in the denominator, that is 4. Okay, so now I draw the F distribution again, equals F dot dist. So now I link to the first cell, 0. Now I navigate where I put the numerator degrees of freedom, 1. Press F4 so that it is fixed. Now you link to the degrees of freedom in the denominator. You also F4 that. And then we just want the probability density function, so that's a 0. And as I said, for 0 we get the number is not available. But now we can copy down that formula, and where it says number doesn't exist, I just replace by NA. Okay, so now let's take a look at the distribution. Go to Insert, Recommended Chart, and maybe here. So maybe let's format the axis a little bit nicer. On tick marks, maybe 10. Labels also every 10. All right, so now we have our distribution, and you see, it doesn't look like a normal distribution. But let's say if we had more degrees of freedom in the numerator, meaning we have more coefficients, maybe let's say 10, or in this case we would have 11 coefficients, and the degrees of nominator is maybe we have like 1,000 observations. So you see that even the F distribution approaches the normal. Okay, so, but the idea of conducting an F test is similar to any other test that we pursued. And I want to show you also again, lastly, when we go to our regression results, which we had here. So you see, for the statistics of the F, we get an F probability of 0.041, which is exactly the same for the slope coefficient. So that's an interesting finding that somehow already shows you that there must be a relationship between all those distributions. And of course, there is a relationship, and they somehow are all derivatives of the normal distribution. But yeah, so now we know where we get such an ANOVA table from, and we know what the mean sum of squares and the 22, that's a 22 over 1, 10 over 4, F statistic 22 over 2.5, what that all means. And yeah, so those are the steps that you conduct in an F test, and that is typically the last thing that you do in a regression analysis. So you want to know, is the model in its entirety significant? Okay, so we'll stop here with the theory, and then beginning with the next topic, we just want to talk a little bit more about the steps that you have to do when you actually run a regression. But let's just stop here, and I'll see you in the next video, hopefully.